Hi everyone, I am Kyuhan from KAIST, and I'll present our work SLUGGER, Lossless Hierarchical Summarization of Massive Graphs. This is a joint work with Jihoon and Kijung. Graphs are a natural and powerful abstraction for representing relations. Social networks, hyperlink networks, and online curation networks are well-suited examples. They have millions or even billions of nodes and edges, and their numbers are rapidly growing due to the proliferation of the web and its applications, which produce a large amount of data ceaselessly. However, despite the abundance of graph research, many existing graph algorithms silently assume that the input graph fits in main memory without causing I/O delays to the disk or over the network. Thus, existing graph analysis tools are inapplicable to large-scale graphs that do not fit in main memory. Consequently, several graph compression techniques have been proposed to store such large graphs efficiently, such as the web graph framework, graph summarization, node relabeling schemes, and pattern mining. This work focuses on lossless graph summarization, where nodes with similar connectivity are combined into a supernode so that their connectivity can be encoded together to save bits. Here is a brief example of how graph summarization summarizes the original graph into a summary graph. The unweighted input graph G is represented by edges between supernodes, which roughly describe the input graph. And for exact restoration, the difference from the input graph is stored separately in the form of edges to be added, which we call positive edges, and edges to be removed, which we call negative edges. Graph summarization stands out among graph compression approaches due to the following advantages. First, its outputs are graphs, and thus they can be further compressed using any graph compression techniques. In other words, graph summarization can be used as a preprocess to give additional compression. Moreover, the neighbors of each node can be retrieved by decompressing on the fly only a small fraction of an output representation. This enables various graph algorithms such as DFS, PageRank, and Dijkstra's to run directly on output representations without decompressing the entire graph. However, despite its effectiveness, there do exist limitations on the graph representation model of graph summarization. That is, each node should belong to exactly one supernode. This limits the summarized graphs from exploiting hierarchical relationships between nodes, which are pervasive in real-world graphs. Various networks, including web graphs and biological networks, are hierarchically organized. Such hierarchical structures have been exploited for algorithm design, including those for community detection and realistic graph generation. However, the existing graph summarization model cannot express and thus exploit hierarchical structures for compression. We propose the hierarchical graph summarization model to address the aforementioned problem, which generalizes the previous graph summarization model while inheriting its advantages. Our new model is capable of naturally and concisely representing hierarchical structures. In addition, we propose SLUGGER, a fast and effective lossless hierarchical graph summarization algorithm for concisely and exactly representing a given graph under our new model. Here is an outline for the presentation. I will first introduce the hierarchical graph summarization model. Then I'll introduce our algorithm, SLUGGER, which concisely and exactly represent a given graph under the hierarchical graph summarization model. After that, I will share experimental results. Lastly, I will wrap up the presentation with our conclusions. In this work, we consider as an input a simple undirected graph G, where V denotes the set of nodes and E denotes the set of edges, and we use pairs to denote undirected edges. We call nodes and edges in G subnodes and subedges respectively, to distinguish them from supernodes in the proposed model. Before introducing our proposed hierarchical graph summarization model, we would like to review the previous graph summarization model formally. The graph summarization model describes a graph using three sets of parameters. The first set of parameters is a set P of edges between supernodes S, which indicates the edges between all pairs of nodes in the two supernodes. The other parameters are for corrections. A set C plus of positive edges indicates the edges in the input graph but are not described by P. A set C minus of negative edges indicates the edges described by P but not in the input graph. Importantly, supernodes should be disjoint, and in other words, each subnode should belong to exactly one supernode. Now I'll introduce the differences between our proposed hierarchical graph summarization model and the previous graph summarization model in the next two slides. The main difference is whether supernodes can have a hierarchy. Supernodes from the previous graph summarization model should be disjoint, and each subnode should belong to exactly one supernode. Thus, any hierarchy among supernodes is not allowed. However, in our proposed hierarchical graph summarization model, each supernode may contain smaller supernodes. We provide an example hierarchy among supernodes. Note that subnode 2 is included in both the root supernode and an internal supernode. Allowing such hierarchical relations between supernodes helps concisely represent relations between nested communities within the input graph. However, note that our model does not allow partially overlapping between supernodes. That is, any supernode cannot have two parents. As a result, parameters are also different in the models. The hierarchical graph summarization model describes a given graph G using a set of H hierarchy edges between supernodes S, a set P plus of positive edges between supernodes, and a set P minus of negative edges between supernodes. From now on, we'll call positive edges P edges, negative edges N edges, and edges in H edges for simplicity. A P edge between two supernodes indicates that edges should be added between all pairs of subnodes between the two supernodes. And an N edge indicates that edges should be removed between all pairs of subnodes between the two supernodes. More precisely, there exists an edge between two subnodes in input graph G if and only if there are more P edges than N edges between the supernodes that they belong to. And here is a toy example of how our model retrieves the original graph from the summarized graph. Let's say we're retrieving the neighbors of subnode 0 in the input graph. Only P edges exist between subnodes 0 and 1. Thus, 1 is a neighbor of 0. However, one P edge and one N edge exist between 0 and 2. Thus, 2 is not a neighbor of 0. Finally, 2 P edges and 1 N edges exist between 0 and 3. Thus, 3 is a neighbor of 0. Then how do we summarize a given graph using the hierarchical graph summarization model? Here is an example procedure of hierarchical graph summarization. Let's say we're given an input graph with 7 nodes and 14 edges. P edges are colored red in the top panel, and N edges are dotted in blue. H edges are colored black in the bottom panel. The procedure is lossless, and in every step, the three types of edges exactly describe the input graph. As 0 and 1 are merged, a new supernode A is generated at the expense of 2 additional H edges, which indicates the hierarchy between supernodes. 8 edges previously incident to 0 or 1 are concisely represented with only 4 P edges. In the following step, subnodes 2 and 3 are merged. Again, as 2 and 3 are merged, a new supernode B is generated at the expense of 2 additional H edges. 7 edges previously incident to 2 or 3 are concisely represented with 3 P edges. In the following step, supernode A and supernode B are merged. Again, as A and B are merged, a new supernode C is generated at the expense of 2 additional H edges. The self-loops at A and B and the pH between A and B are concisely represented with a self-loop at C. Other edges previously adjacent to A and B are succinctly represented with one pH and one N edge. The pH between root supernode C and leaf supernode 5 indicates subnodes 0, 1, 2, and 3 are adjacent to subnode 5 in the input graph, and the N edge between internal node B and leaf supernode 5 indicates that among them, 2 and 3 are not actually adjacent to 5. In the last step, internal supernode A is removed. Note that removing this internal node does not affect the reconstruction of the original graph, but reduces the number of total count of edges. Note that the total count of edges decreases from 14 to 10 as summarization progresses. The lossless hierarchical graph summarization problem, which we consider in this work, is an extension from the previous graph summarization problem, which is formulated in the upper part. Given an undirected graph G, their goal is to find the summary graph that minimizes the total count of edges. This is because the number of bits required for storing a summary graph is roughly proportional to the count of edges in it. Our newly defined hierarchical graph summarization problem is formulated in the lower part. Given an undirected graph G, our goal is to find the best hierarchical summary graph that minimizes the total count of edges. Our model generalizes the previous graph summarization model by including it as a special case. In other words, all types of edges of the previous model can be expressed by the types of edges in our model. Thus, the hierarchical graph summarization model can always describe a given graph more concisely than at least as concise as the previous model. Here, we provide an example where our model can be strictly more concise than the previous model. Please refer to our paper for details. Now I'll introduce SLUGGER, our proposed optimization algorithm for the lossless hierarchical graph summarization problem. Given an input graph G, the maximum number of iterations T, SLUGGER produces a summary graph G bar that minimizes the encoding cost, which is measured by the total count of edges. SLUGGER first initializes G bar to G. Each subnode in G is regarded as a supernode in G bar. Similarly, each sub-edge is regarded as a p-edge. N edges and H edges are initialized with empty sets. SLUGGER repeatedly merges supernodes and updates their encoding at the same time. To this end, SLUGGER runs the candidate generation step and the merging step alternatingly. The candidate generation step reduces the search space, and the merging step selectively merges nodes if the encoding cost is reduced. After repeating the above steps t times alternatingly, SLUGGER executes the pruning step to reduce the encoding cost further. After the pruning step, the current hierarchical summary graph G bar is returned as the final output of SLUGGER. Now let me describe each step in detail. SLUGGER divides root nodes into disjoint candidate sets and searches root node pairs to be merged within these candidate sets. This is because naively finding a root node pair whose merger gives the largest reduction in the encoding cost needs to take total number of root nodes, choose 2 pairs into consideration. To generate candidate sets rapidly and effectively, each candidate set should consist of a small number of root nodes, and node pairs within each candidate set should be likely to give a large reduction in the encoding cost. Our strategy is to group root nodes within distance 2 as a candidate set, because merging 2 root nodes with 3 or larger distances always increases the encoding cost. To this end, we employ min hashing. Let me move on to the merging step, where SLUGGER merges nodes selectively within each candidate set. In the merging step, SLUGGER greedily repeats merging root nodes and at the same time updating the encoding accordingly. For each candidate set D obtained from the previous step, SLUGGER randomly repeats selecting one root node A and finds B, then maximizes the saving within D, where saving is the ratio of reduction in the encoding cost. If the saving exceeds a threshold theta at iteration T, SLUGGER merges A and B and updates the encoding. Due to the threshold, selected root node pairs are not merged if merging them does not reduce the encoding cost much. Thus, pairs with a larger reduction can be merged first. To select the best root node pair among candidates, SLUGGER needs to compute the amount of saving by temporarily merging pairs of root nodes. Moreover, when two root nodes are merged, H edges, P edges, and N edges need to be temporarily updated so that the encoding cost is minimized. However, even when the hierarchy between supernodes is assumed to be fixed, it is still computationally expensive to exactly minimize the encoding cost. Thus, when two root nodes are temporarily merged, SLUGGER relies on a suboptimal encoding obtained by focusing on a small number of supernodes, specifically the merged nodes, neighbors, and their direct children in the hierarchy. By doing so, there are a constant number of possibilities, and a valid one reducing the encoding cost, most among them can be exhaustively searched. Let me move on to the pruning step. In the pruning step, SLUGGER further reduces the encoding cost by removing supernodes that do not contribute to succinct encoding. That is, SLUGGER prunes a supernode if all incident P edges, N edges, and H edges can be replaced with while decreasing the total encoding cost. In detail, the pruning step is divided into three substeps. First, SLUGGER removes each non-leaf node that is not incident to any P or N edge. By doing so, we can reduce the number of H edges by 1 without losing any information. Second, SLUGGER removes each non-leaf node with only one incident non-loop P or N edge. By replacing the edge with the edges to the direct children of the removed node, we can always reduce the encoding cost by at least 1. Moreover, a further reduction can be achieved when we can cancel out edges of different types, as in the example below. Lastly, we try partially using the result of SWAG, which is the state-of-the-art non-hierarchical graph summarization method. This is possible since the previous graph summarization model is a special case of our model, as explained earlier. Since P and N edges incident to internal nodes are removed, this step may enable more supernodes to be pruned by the previous steps. Therefore, these three pruning steps are repeated a few times. Let me share our experimental results. We performed experiments on 16 real-world graphs with up to 0.8 billion edges. The datasets used include hyperlinks, social networks, collaboration networks, and email networks. We compare SLUGGER with 4 algorithms for lossless graph summarization: randomized SAGS, SWAG, and MOSO. We compared the size of the output representations obtained by SLUGGER and its competitors. SLUGGER provided the most concise representations in all 16 considered real-world datasets. Especially, SLUGGER gave an up to 29.6% smaller representation than the best competitor in the protein dataset. On average, SLUGGER gave a 13.5% smaller representation than the best competitor in all 16 datasets. In terms of speed, SLUGGER was comparable with SWAG, which consistently provided the second most concise representations. Specifically, SLUGGER was faster than SWAG in 7 out of 16 datasets, while SAGS was fastest in 15 out of 16 datasets. By rapidly deciding nodes to be merged, its output was least concise in the same number of datasets. In terms of scalability, SLUGGER scaled linearly with the size of the input graph, as proven theoretically in the paper. Moreover, only SLUGGER and SWAG successfully summarized the largest graph with about 0.8 billion edges, while all others failed. In addition, we conducted additional experiments regarding the effects of iterations, pruning, and bounding the height of hierarchical trees. For details, please refer to the appendix of our paper. Here are two main contributions of our work. First, we proposed the noble hierarchical graph summarization model, which naturally exploits prevalent hierarchical structures in real-world graphs, and also generalizes a widely used graph summarization model. Moreover, we proposed SLUGGER, a linear time algorithm for summarizing large graphs with the new model, and we showed that SLUGGER outperforms state-of-the-art competitors. The source code and datasets can be found in the provided URL. And here are the references. Please check out our paper for more details. Thank you for listening.